All right, chapter 13 is all about gravity. So we're going to talk about gravity now. The good thing about this chapter is it actually brings together a whole lot of the concepts that we've been learning about all semester. From forces and motion, to circular motion, to conservation of energy, to conservation of angular momentum. All that gets tied together when gravity, when you talk about satellites and things orbiting other objects. So, we're going to start with Newton, where we usually start. The story goes that Isaac Newton was in his grandfather's orchard, and he saw an apple fall. And I'm sure everybody's heard about this story. The story has later become that the apple hit him in the head, but I don't think that Newton ever said it hit him in the head. But he did see the apple fall, and that was his inspiration for gravity. And what the rest of the story is, it wasn't the apple falling. It was the idea that the force that was making the apple fall was the same force that was holding the moon in orbit around the Earth, that was holding the Earth in orbit around the sun. That all of this was one single force, the force of gravity. And so that's why he called it the law of universal gravitation. Because up until that point, this is in the 1600s, they thought that there were one set of science rules on the Earth, and then the heavens had their own rules. And the heavens rules were different because the heavens were supposed to be perfect. And Newton was the first one to say, no, the laws of physics are the same everywhere in the universe. And that is one of our fundamental assumptions in all of science and in astronomy and physics, is that the laws of physics are the same everywhere in the universe. They never change. And if it's going to be a law of physics, it has to work everywhere in the universe. Okay? Now, we can't prove that, but we've never seen anywhere in the universe where our laws of physics seem to not work. So we think it's a good assumption just by going that way. But you can't prove that. You can't go everywhere and make sure that it always is going to work. But Newton realized, and he came up with the formulation of gravity, and says the force of gravity is equal to g. This is his constant. In fact, we call it Newton's gravitational constant, times the mass of one object times the mass of the other objects times the distance between their center of mass is squared. So this is Newton's gravitational constant. And this is a very small number. It's like 6.86 times 10 to the minus 8 or something like 10 to the minus, 6.67 times 10 to the minus 11. And it has units of Newton meter squared per kilogram squared. So that this is kilograms and kilograms, so kilograms times kilograms is kilograms squared. That will cancel with this. And this is meter squared, which cancels that, and you're left with newtons, which is the force of gravity. Okay? So this is just a number. And that number has been very well determined. Okay, it goes out to many, many, many decimal places, but that's all we're going to worry about in this class. We only have about 2 or 3 significant figures. These are two masses and the distance between their center mass. So if I have one mass here and another mass here, big M and little m, the distance between them, this is r. Okay, it's between their center of masses. And notice it's squared. So it falls off as the distance squared. Meaning, if you think of it in our solar system, the Earth is at 1 AU from the Sun. Well, Saturn's at almost 10 AUs, about 10 AUs. So it is feeling 1/100th the gravitational pull from the Sun because it's 10 times further away and that 10 is squared. So gravity never stops. It just falls off as the distance squared. So the further you get away, the weaker and weaker gravity gets, or the pull you feel from that. All right. Now, let's think about this. This is the force of gravity, right? This is what's called your gravitational mass. But Newton also said, in his second law of motion, that force is equal to ma. And question is that mass the same as that mass? That has been experimentally determined, and to as good of data as we can get, we find those are exactly the same. Meaning that the gravitational mass and the inertial mass are exactly the same. There's no proof of that, but it seems to be the case. So we assume that is also the case, that these are exactly the same mass. But let's think about this. So if this is a force, we can plug this in here. We can say, oh, well, ma is equal to g mm over r squared. Now let's say we do it for an object falling on the surface of the Earth, like a tennis ball that you drop. Okay? Then what happens is, this is the mass of the tennis ball times its acceleration is equal to g times what's pulling it down. It's the whole mass of the Earth times the mass of the tennis ball divided by the radius of the Earth squared, because that's how far it is from the center of the Earth, or the center mass of the Earth, to the center mass of the tennis ball. Look, those cancel out. So you divide through by that, and we're left with the acceleration is a constant times a constant divided by a constant squared. And that's where we came up with that a is what we're going to call little g, and this is just equal to gme over the radius of the Earth squared. And if you put in all the numbers, that's where we come up with 9.8 meters per second squared, 9.81 meters per second squared. This is a constant for the Earth. Now if you go to a different planet or the moon, then the masses and the radiuses are going to change, and that's why your gravitational acceleration on that object is going to change. If you're on the moon, your gravitational acceleration is about 1.6, or about 1/6 what it is here on the Earth. So everything falls significantly slower. And when you watch the videos of the astronauts that were on the moon and they drop rocks, or they are running around, well, kind of running, they kind of do a hopping thing, the acceleration is significantly lower than it is on the Earth, which made it good too, because they didn't have to have giant rockets to get back off of the moon. So that was one advantage. Is it's hard to get off the Earth because we got a lot of gravitational pull. It's easier to get off the moon. All right. This also shows what Galileo had figured out, that it's independent of the mass. When you drop an object, as long as there's no air friction, it's going to fall at exactly the same acceleration. Okay? Galileo figured this out by actually dropping objects, and he realized if they were about the same size and shape, if they had different masses, they would still fall at the same rate. So it wasn't the mass that mattered. It was that the acceleration was going to be the same. All right. Now, we're going to talk about objects in orbit. So we have to go back and learn about Kepler's laws of planetary motion. Now, Kepler was alive. Johannes Kepler was alive long before Newton. Well, not long, about a lifetime before Newton. Kepler was alive at the exact same time Galileo was. And if you can remember right, Galileo died, the same year that Galileo died was the year that Newton was born. So it helps keep you in perspective there of how these things come in history. So Kepler, Johannes Kepler, was, well, he has an interesting life. He came from a very large family. His mom was tried as a witch, survived as they ran out of town to get away from that. He had many brothers and sisters. His father was gone. He was a mercenary. He got killed in action. So he had a really crazy life. But he was very into mathematics and figured out how planets moved. And so he went to the guy in the world at the time, a man named Tycho Brahe, that had the best data on the planets, and he decided he wanted to figure out how they were going to work. And so he did elaborate studies of trying to figure this out, and it took him many, many years, like 20-some years before he figured this out. But eventually he figured out how all the planets move. And he came up with his laws of planetary motion. And as is typical, he had 3 laws of planetary motion. I don't know why, but it seems like everything comes in 3. His first law was that all planets orbit on elliptical orbits with the sun at one focus. All right, so let's talk about ellipses. All right, this is an ellipse. Remember, ellipse is just an oval, or technical terms, from a mathematic perspective. An ellipse is part of what they call a conic section. If you have a cone and you cut it at an angle, you can create an ellipse. But to define an ellipse, you have the long axis, which we call the major axis, and you have a shorter axis called the minor axis. And the definition of ellipse says that, switch to video 2, I'm running out of time.